In this video, we want to get into a little bit more about exactly how first-order differential equations are solved. We'll start with first-order differential equations because they're the most straightforward equations to solve and can often be solved by pretty straightforward methods of integration. So this is the outline of the chapter out of ZIL. We will not cover all of the sections here. We're going to skip section 1. We'll talk about separable equations, linear equations, exact equations, and maybe brush very briefly on solutions by substitution. And that's pretty much all we'll really cover in this chapter. So first let's look at what is meant by an equation is separable. And first of all, the thing that makes separable equations desirable is that if you have an equation that is separable, it can be solved by simple integration. So first of all, and remember we're dealing only with first order differential equations. So we have some derivative dy dx that in general is a function of x and y. Now in the case where this function of x and y does not depend on y, so in other words dy dx is some function of x only, we can then solve this by integration. So basically what would happen would be you would multiply for this equation right here. Let's get a pen. For this equation right here, you would multiply both the left and the right side by dx, yielding the equation that dy is g of x dx. And then if you integrate both sides, you can generate a solution that some function large g of x plus c, where c is a constant, and g of x is big G of x is the indefinite integral of little g of x. Now, some functions that are termed non-elementary don't have an antiderivative that is an elementary function. And in that case, which is unusual certainly unusual for anything that we will do in this class, in that case you would have to leave this expressed as an integral because its indefinite integral may not exist in closed form. But for everything that we will look at, we should be able to take this y is the integral of g of x dx and make that big G of x plus c some constant. So continuing on to define what is a separable equation. So a first order differential equation that's given in this form, dy dx is some function of x only multiplied by some function of y only, is said to be separable or have separable variables. And we can rewrite that in the following way. So basically to get from this expression to this expression, we're multiplying both sides of the equal sign by dx, and then we're dividing by this function h of y, and we're expressing 1 over h of y as p of y. So if you do that algebraic manipulation, you get some function of y times dy is equal to some function of x times dx. And so now this becomes integrable. We can integrate the left-hand side and the right-hand side, and we should get an expression that places y in terms of x. So here are just a couple of examples. If you look, we'll look at example 1 first out of the textbook. So we have this equation 1 plus x times dy minus y dx is equal to 0. And one way to think of this is we want to group all the y terms together and all the x terms together. And so then that will give us an equation that we can separate. So if I move this y dx term over to the right-hand side of the equal sign, and then divide both sides by y and divide both sides by 1 plus x, I end up with this equation. dy over y is dx over 1 plus x, just from the algebra. And then given that, I can integrate the left-hand side and I can integrate the right-hand side. And if I have an integral table handy, I can just look that up on an integral table, or perhaps you remember this integral, but basically this is the natural log. So I have the natural log of magnitude of y is equal to the natural log of the magnitude of 1 plus x plus c1, which represents the constant of integration. So then you might remember that from the laws of exponents, that if you take the left-hand side and the right-hand side and you and you take e to the left hand raised to the left hand side power is equal to e raised to the right hand side power. E raised to the natural log of any quantity just is that quantity. So it basically gets the quantity y back. And then in the second, on the right hand side, we'll have this entire thing in the exponent of the exponential e. And then remembering some of the rules of exponents, that the exponent raised to a sum is the product of the exponent raised to each component of the sum. So I can rewrite this sum, ln of 1 plus x plus c1, as e to the ln of absolute value 1 plus x times e to the c1. And then this, of course, applying the property of exponents, just becomes the absolute value of 1 plus x. And then you have to think about what to do with these absolute value signs, because obviously y could be negative, x could be positive or negative, y can be positive or negative, and just depending on the relative combinations, we could come up with a plus or minus sign here. Now, because we still have a constant here, e to the c1, and we've got plus or minus e to the c1, and c1 is a constant, we can just incorporate the plus or minus and the e to the c1 into a generic constant c. And so our solution then becomes y is equal to c times 1 plus x. And this is standard practice. If you have constants, for example, inside a sinusoid or exponentials raised to constants, it's fairly common to just express that as a constant c without showing the constant inside or as a power. So that's basically how you solve a separable differential equation. So remember, the first goal is to get all the things, all the y's on one side of the equal sign, all the x's on the other side of the equal sign, and then you should be able to integrate both sides. This is another example of a problem, only here we have an initial condition that's been specified, which should allow us then to solve for the constant. So basically we're given this equation. This is our differential equation, and then we're told that when x is equal to 0, y is equal to 0. So y of 0 is equal to 0. So remember, the goal here is to get all the y's on one side and all the x's on the other side. So we're going to take this y term and divide by it, and then we're going to take the cosine of x over dx and divide by it, which is going to flip it over. So once we do that algebra, we'll have this e to the 2y minus y term over e to the y times dy, and then we'll have the sine of 2x divided by the cosine of x times dx. And so now we'll integrate the left-hand side and the right-hand side. And so the first thing to do before integration is to simplify the left-hand side. So e to the 2y over e to the y is just e to the y, and minus y over e to the y is y e to the minus y. So that works pretty easily. And then realizing that the sine of 2x is 2 times the sine of x, we can make that substitution as well. And then integrating both sides. So the left-hand side can be integrated by parts, or this is a very standard integral, this y e to the minus y on any integral table. You should be able to look that up and just pull directly from the table. The right-hand side is also a very simple integral, sine going to minus cosine, and then we have c, the constant. All right, so let's go back now to our initial condition. Our initial condition says that when I plug 0 in for x, I should get 0 for y. So if I come to my equation here, and I put 0 in for x, and I put 0 in for y, then basically what I end up with is that c should equal to 4. I'll get a minus 2 here, I'll get a 1 here, a 1 here, a 0 here. When I combine all those terms and solve for c, I get c is equal to 4. So now we come back to our expression and substitute in 4 for c, and so now we have a solution that does not depend on a constant. So 2 examples of how to solve first order differential equations by separation of variables.